Hello guys, this is a digital assignment submitted to Council of HP, Professor of Data Structures and Algorithms. My digital assignment is on my research tree. Okay, let's continue on the video. So now we are discussing about data structures. The data structures are of two types: primitive, non-primitive. Primitive are like int, char, float and pointer. These are the basic types. Now the non-primitive ones are arrays, tags, queues, graphs, trees, links and files. So subdivided to them are linear and non-linear. These are the linear ones, arrays, tags and queues. The non-linear ones are graphs, trees and linked list. Your files. So hope that you are clear. Next, so we'll go in a flow like this. First, the tree, binary search tree, and operations in it, traversal, insertion, deletion, types and applications. And somewhere here we will have complete search also. Okay. Trees are of two types. One is a normal tree and one is a binary tree. So the normal tree is the one in which node can have any number of children, even 0 also is impossible. But the node must only have one parent. Only one parent. See, as you can see in the example, this node has 3 children and this one has 0. That's it. Continue on. Binary tree is a tree with only 0 or 2. 0 to 2 children per node. So you can say that 2 is the maximum number of children each node can have. So 2 is the maximum number. It can have 0, 1 or 2, but not greater than 2. Hence it is called a decision making tree. Good. Now let's continue on. Here the terminology used is root, which sorry about that. So let's look at this picture here. See, nodes here are of 3 types: root, interior, leaf. Roots are the uppermost one, whereas the leaf are the lowest most one. So roots have no parents, leaf have no children, whereas interior consists of both. Hence root no parent, leaf no child, interior non-leaf, because leaf doesn't have children, interior has children. Height means the distance from root to leaf. We can also say that the levels it is to be divided to like 1, 2, 3. As the height here is 3. Continue on next. Binary search tree. The key point in the binary search tree is that smaller values goes to the left subtree, larger values into the right subtree. Note this point, which is very important. Smaller values in the left subtree, larger values in the right subtree. Here the example is C, like if we consider x, y and z, x is the parent node and y and z is children node. X must be greater than y, x must be less than z, as you can see here. So for the examples, these both are binary search trees and you can verify them also. 10 is greater than 5, less than 30, 5 is greater than 2, 10 is greater than 25, 10 is less than 45, 5 is greater than 2, 5 is less than 45, 45 is greater than 30, 30 is greater than 10, 10 is less than 25. Whereas here this is not a binary tree, as you can see, as this specifically 30 doesn't follow our key point. You can see that 30 is not greater than 45, but still it's in the right side, so hence this is not a binary search tree. So the differences between binary tree and binary search tree are As we have already seen, a binary search tree is simply a tree in which each node can have at most two children. A binary search tree is a binary tree in which the nodes are assigned values with the following restrictions: no duplicate values, the left subtree of a node can only have values less than the node, the right subtree of a node can only have values greater than the node. See, these both are the key points we have discussed earlier. The left subtree of a node is a binary search tree, the right subtree of a node is a binary search tree. So it continues on. Okay, going on next. So the operations in binary search tree. So the operations in binary search tree are transversal, search, insertion, deletion. Okay, in transversal there are another three types: pre-order, in-order, post-order. Search there are of two types: iterative search, recursive search. They both differ in the algorithm but both mean pretty much the same: insertion and then deletion. Okay, so let's start with traversal. Pre-order traversal, in-order traversal, post-order traversal. See, in pre-order traversal we start from the parent and go to the left subtree, then come to the right subtree, then go again to one. See, the number should not be repeated in any traversal, and that's it. See, same as pre-order traversal, here but a little bit different. We start here with the left subtree, go to the parent, and then return to right. Post order, similar way, but we start with left subtree, go to the right subtree, then return to the parent. So let's see an example to clear it out. Pre-order transversal. As we have discussed, we first start with the parent 23, then go to 18, then after go to 12, and we come to this way, but 18 is already taken, so we have to get back to 20. Then after we again go back here, but 23 is already taken, so we go to 44, then come back here to take 35 and go back here, but 44 is already taken, come back here 52, 44 already taken, 23, return to the same position. And so check it: 23, 18, 12, 20, 44, 35, 52, exactly the same. If you didn't understand the way we go in, here is the way we did go in. We started from 23, went to 18, then to 12, then got it back to 18, but 18 was already taken, returned to 20, okay, got it back to 23, but 23 was already taken, got to 44, which is not taken, so take it 35, return to 44, but only once we can take a single value. 52, take 52, return to 44, return to 23. So this manner we travel. Sorry, this manner we travel. Okay, now the post order transversal will start from 12, go to 20, then 18, then 35, 52, 44, 23. See, this may be a little confusing, but remember what I told you, like 2 months before. See, remember in the way we go in, we go from 1 to 3. Don't forget that. So we start from 12, go to 20, then to 18, then to 35, then to 52, then to 44, then last 23. Okay, so wait a second. Okay, now it's fine. See, for a bit more clear expression, see, look here. First, take out all the leaves. Not take a leaf and delete it from the tree. So, for example, now 12 is the point where we begin from. 12 is a leaf. So, what we do is take 12 and delete 12. So, we can do like, so I remove 12 and keep the 12 here. Next leaf is 20. So we remove 20 and add it here. As you can see, I have removed 20 and placed it here. Now you can see that 18 is also a leaf now. So we can remove this 18 here too. Okay, now moving on to the next part. We can't remove 23 now because it is not a leaf, because it has children down the line. So the next one we go is 35. As you can see, 35 is a leaf. So now we can remove it. So 35 can be removed. Let me remove that. So now 35 is gone. So next 52 can also be considered as a leaf. So we can remove these leaf too. So now 44 can also be considered as a leaf. But after 44 is removed, only 23 will be left. So first 44, then after 23. So you can check from rewinding the video that this and the, what do I say, the series will match perfectly. Okay, that's it. Oops, I forgot to this. That's it. So the next, as you know, is in order transversal, which is a little bit similar and a bit easier too for the first one. So here, as I already said, let's start from 12, then go to 18, then to 20, then to 23, then to 35, then to 44, then to 52. So actually you can think like, okay, now continue on similar way. We start here too. So but we start from 12, go to 18. As 12 for the first time, we take 12, then 18, then 20. 18 are already been taken, then to 23. But here comes the problem. You don't go to 44. You go to 35 actually here. 35, 44, 52. Then this is all taken. 44, 23 taken, 18 taken. So this is how you do it. So the trick I think will help you out is, wait, let's just wait. This was the original. Put all the values down, like 12, 18, 20, 23, 35, 44, and last 52. See, you can go in a way, in a direction like this. Not only say 12, 18, 20, 23, 35, 44, 52. So in this way, you'll get all the order right. That's it. On to the next. On to the next. This is binary search. So in binary search, there are two types: iterative and recursive. And for both, these are the algorithms given. In binary search, 3 arguments: a and key, l equal to 1, h equal to 1, when l is less than h, bid equal to l plus h by 2. If key equals a of bid, return bid. If key is less than a of bid, h equal to bid minus 1, else l equal to bid plus 1, close the while loop, return 0. Recursive algorithm R bid search, l, h, key, 3 arguments. Open it. If l equals h, a of l equals to key, return l, else return 0. Else bid equal to l plus h divided by 2. If key equals a of bid, return bid. If key is less than of a of bid, return R bid search, l bid minus 1 key, else return R bid search, bid plus 1 h comma key. Close the loop. Okay, let me explain you how the search in a binary search tree works out. See, let us consider this as argument list. Now, for the first time, this will be h, and this will be h, l, h, and bid equal to l plus h by 2. Yeah, it's usually a step operator here, but it worked out pretty well this time. But usually a step operator is better, which is 8, 8. Bid value is 8. But before doing this all, we must have a key value to figure out what we are finding out. Key value to figure out what we are finding out. So let's assume this time it is 42. So we have key as 42, L and H values and bid value. So first we have to check whether here 42 is greater than bid or less than bid. So as 42 is greater than 29, L will become as bid plus 1. So what will happen is, this will happen as you can see. L will be bid plus 1 and H will remain in the same position as you can see. H in the same position, bid in the same position, but L will change. So okay, now as you can see the bid also will change because of this. 9, 15. 9 plus 15 is 24. 24 by 2 is 12. So for 12, what we do is change this bid value. First, this will be 12. I'll change it. There you go. And here the bid will be changed to here. There you go. So bid will be 12, and when compared with the key operator, 42 is less than the bid value. Hence, this time the H will shift. So as we know, as for the algorithm, H will be shifted to mid minus 1. So let me just do that for you. So H will be shifted here. Then again the mid value also will shift, that is 9 plus 11 by 2, which is 20 by 2, that is 10. So this what will happen, but 42 when compared with 36 is again greater, so L will shift mid plus 1. So what will happen is, you can see that L and H got in the same value, that is 42, and then we will key equal to 42, and we have got our answer. Hence completed. Okay, let's get into the insertion in a binary search tree. Before going on to an example, let's look at its algorithm. Algorithm is perform search. Okay, the first step in the algorithm is perform search for value x, which we already learned. Search will end at node y if x is not at 3. If x is less than y, insert new leaf x as new sub 3 for y. If x is greater than y, insert new leaf x as new sub right sub tree for y. So now we do the example. Insert of 20. You can see that 10 is less than 20, so it will go out to rightward. 30 is greater than 20, so it will go leftward. 25 is greater than 20, so it will go leftward. So as no element node is there, so it will create a new node and insert 20 inside it. So this is how the insert operation works in a binary search tree. On to the delete operation in a binary search tree. Okay, same as before, perform search for value x. If x is in the leaf, delete x, else we must delete internal node, replace with the largest value y on the left subtree or smallest value z on the right subtree. Delete replacement value y or z from subtree. Remember, deletions may unbalance trees. So let's look at this example to understand better. Delete 25. So 10 is less than 25. As we know in the search, it goes to right. 30 is greater than 25, it will go to left. 25 equal to 25. We found the element, it will be deleted. So the corresponding next figure will not have 25 elements. But as said before, the tree will be unbalanced. But in this case, it is already unbalanced. So I hope you understand that. Okay. So on to the next slide, there are a large sites of applications for BST used in many search applications where data is constantly entering and leaving, such as the map and set objectives in many language libraries. So we can also say dictionaries. Storing a set of names and being able to look up based on a prefix of a name. These is used in the internet routers these days. Storing a path in a graph and being able to reverse any subsection of the path in big O of log n time. Useful in the traveling salesman problems. So this big O of log n is for most of the cases. For the worst case, it will be usually big O of n. Allows you to do a range searches efficiently. Okay. example video. I thought it could be used as an implementation detail in my research tree. So it's how it works, and there are many real life examples of this which you can Google them. So with this, I would like to end my session. Thank you. So this is the additional course I'm doing, which is suggested by Professor Kausar Ahmed P. So this course is on Coursera, and it is algorithmic toolbox. Actually, this is a 6-week course. So this course mainly teaches us about this essential algorithmic techniques, design efficient algorithms, practice solving algorithmic interview problems, implement efficient and reliable solutions. So this is what the skills we'll gain after the end of this course: dynamic programming, debugging, software testing, algorithms, computer programming. So weekly wise, this is the things we have to study. For week 1, programming challenges; week 2, algorithmic volume; week 3, greedy algorithm; week 4, divide and conquer; week 5, dynamic programming 1; week 6, dynamic programming 2. So it was rated very highly by everyone done by this course. So this is to it. Thank you. The name of our project is the traveling salesman problem and its applications. The members of the team are Sishanga Gharmutla, Raghu Samani, and Pranav Kurana. So our problem aim is to help a salesman visit all the cities in the list, in which he knows the location of all the cities and find the shortest path that he has to visit all the cities only once and returns to the city where he started. The distance and the corresponding path should be displayed as the output. Objective: the object of the salesman traveling problem is, as already said in the aim, he has to visit all the cities at the minimum transportation cost. It is a very challenging problem with a combination optimization. It is one of the most computationally difficult problems. Brute force or exhaustive search can be used to solve this problem, but for larger number of cities, this technique is not feasible. The inputs are the locations of the cities and has to visit in Cartesian coordinate system. However, this coordinates can be converted into adjacent matrix, which will be shown in the code which is presented in the W2. So, going on to the next, we in traveling salesman problem explain the existing methods and its drawbacks. There are many algorithms for this regarding this problem, such as the ACO algorithm, ads quality optimization. By analyzing the ads behavior, the ACO algorithms are designed to search for the shortest path between the nest and the source output. It is a relatively novel technique that has been successfully used in many applications, especially real problems in combinatorial optimization. So ACO algorithm models the behavior of real ad queries in establishing the shortest path between food sources and nests. For such large number of nodes, TSPs are very computationally difficult to solve exponential time to convergence. This is the first drawback. The second drawback is convergence is guaranteed. Convergence is definitely guaranteed, but the time to convergence is uncertain. Another such as the same algorithm is the nearest neighbor algorithm. It starts like this: choose any starting node, consider arcs which join the previously chosen nodes to nodes and next one. Choose the arc with the minimum weight and add this node to the tool. Repeat this until all the nodes have been added, and the arc will join the last to the first. So its drawbacks are: it may lead to an incomplete tool. The algorithm does not necessarily give the best solution. It chooses the best route at each node without considering future testing problems. Another one is a genetic algorithm. Genetic algorithm is used to solve an optimization problem at TSP. As the number of cities increase, the amount of computational time to solve this problem grows exponentially. These algorithms demand innovative solutions if they are to be solved with a reasonable amount of time. So this algorithm have each own drawbacks. So which in this project we are trying to use dynamic programming and brute force algorithm. So solution of TSP using brute force algorithm. The algorithm is get the input of the location of all the cities as coordinates and store them in a list. Create a new index list which contains the index of cities. Find all possible permutations to the index and store all lists in another list. From all permutations of the index list, find the total distance between all the cities corresponding to the permutation of index list. Find the index list whose list corresponding to distance is minimum. The minimum distance is the shortest path, that index list is the shortest path. I'll repeat it again. The minimum distance is the shortest distance path and the index list is the shortest path. So this programming, I mean this not dynamic, this one is also called as exhaustive search. This problem is feasible when there are less number of cities. When the number of cities increase, it's little problematic to use this. So if there are n cities, then the total running time of the problem will be big of n factorial. So continuing to dynamic programming. So the algorithm goes like this. Let the given set of vertices be 1, 2, 3, 4, so on, comma n. Let us consider 1 as a starting and the ending point for the output. For every other vertex I other than 1, we must find the minimum cost path with 1 as a starting point and I as the ending point, and all the vertices appearing exactly once. Let the cost of this path be cost of I, and the cost of corresponding site will be cost of I plus distance of I comma 1, where distance of I comma 1 is the distance from I to 1. To calculate cost of I using dynamic programming, we need to have some recursive relation in terms of subproblems. Let us define a term C of S comma I to be the cost of the minimum cost path visiting every vertex in the set as exactly once, starting at 1 and ending it at I. We return to the minimum cost of all cost of I plus distance of I comma 1 values. So we will be also converting coordinates of city to adjacent matrix. Hence, so we will use the data structure we'll be using is a 2D array, and the implementation language will be C program. Going on to the advantages, dynamic programming, usually referred as DP, is a very powerful technique to solve a particular class of problems. It demands very elegant formulation of the approach and simple thinking. The idea is very simple. If you have solved a problem with the input given, then the results from the future reference, so as to avoid solving the same problem again and again. If the given problem can be broken up into smaller parts and the given subparts to more smaller, and in this process you will observe some overlapping subproblems, then this is a big hit for dynamic programming. Also, the optimal solution to the subproblems contributes to the optimal solution of the given problem. When we use a dynamic programming algorithm to find an optimal solution for a traveling sensor problem, we have the following advantages. We don't use linear programming techniques. We don't use goal and parametric programming techniques. The proposed method is very easy to understand and apply. So going on to the next thing, the testing is given in the review 2 of the document, and it is submitted to Council of Hamid, and the time complexity of this equation turned out to be big O of 2.8 into n square if they are total in n cities. Thank you. Here comes the end to this presentation. Thank you for listening to this.